Alright, starting in talking about alcohols and elimination reactions. Just like always, this R group is referring to some kind of a carbon chain. And then we're learning about a new functional group, and that's this OH group, which is known as the hydroxyl group, and it makes it an alcohol. Have to think about this just a little bit different. Up until now, you would have seen the hydroxyl group, and you would have called it a hydroxide. Now that would be an OH minus. It's a polyatomic ion. When we're dealing with an alcohol, that's not what this is. It is not a base. It's not a hydroxide group. It is a hydroxyl group. It sounds about the same, just to make life miserable for all of us. Now, small alcohols, in terms of short R change, short carbon chains, are liquids at standard temperature, at room temperature. Longer chain alcohols will become waxy solids. Alcohols themselves, they boil at higher temperatures than hydrocarbons that have comparable molar mass. And so if we had something like C3H8, and we compared that to something like C2H5OH. Okay, so here we've got 18 plus 8. Sorry, let's try that again. 12.01 times 3 plus 8 times 1.01. Here we've got something that's going to be similar, not identical. Pause this for a moment. Look up boiling points on Wikipedia. This is propane, this is ethanol. Look up boiling points. You're going to notice a difference, and this would work for other ones as well. We could even pick a lighter alcohol than C3H8. Even compare C4H10. Okay, so compare butane in any of its isomers to even methanol, H2, sorry, H3OH. Terrible 3. Alright, anyways, if you compare those, again, look it up on Wikipedia, find boiling points. You're going to see that in both cases, in all of the cases in fact, the alcohols will have a higher boiling point. This is due to the fact we have this OH group forming hydrogen bonds. If you think back to that section of Chem 20 that nobody likes, if we look at this structure, and I'll just do methanols because that's easy to draw. Okay, so if we look here, what we would see is this oxygen here, and you don't normally show this, but this oxygen here has lone pairs. And these lone pairs, because oxygen is so electronegative, they can form very strong intermolecular hydrogen bonds with a neighboring hydrogen attached to the OH, or attached to the O, I should say. Okay, anyways, we get the big thing here is you get hydrogen bonds, which means the boiling point is much higher. Okay, now how do we make alcohols? We'll talk a little bit more about these, but it's going to be a reaction. It's an addition reaction. We can actually react alkenes with water. Okay, we need a catalyst, but we take our alkene, and the way that this works, I'm not happy with this picture here entirely, but this H ends up joining up to this C, and then our OH ends up attached to the other C. Okay, we break the double bond here. We use one of the electrons from that double bond to bond to our hydrogen. This bond between the hydrogen and the oxygen breaks. The other electron from the double bond then is used to bond to the oxygen. Okay, we've made an alcohol there using an addition reaction. Now, how do we name these things? Alright, we're going to identify first the longest chain that includes that hydroxyl group. Okay, you're going to name the parent alkane or figure out what it is. So if it's a 5-carbon chain, you're going, okay, that's a pentane. You're going to drop the E from the alkane name and add the suffix OL. So it becomes pentanol. Okay, so again, let me just show here. E, that's a terrible straight line. Let's try again. Right, so here, again, we have 1, 2, 3, 4, 5 carbons. Okay, this OH is attached to the number 2 carbon. So far we haven't got there yet. We drop the E from this and we add the term, the letters OL. If necessary, add a number or numbers to communicate where the hydroxyl group is, or if there's more than one, where they are located in front of the ol. Okay, this is at the 2nd carbon position. And so this is going to be, let me just type it out here for you. Assuming my computer wants to work, there we go. Oops. Pen10-2-all. Okay. We drop that E because there's after the 2, there's a vowel. If we had, for some reason, and let me just make another picture here real quick. 1, 2, 3, 4, 5. If we have this. Okay, so again it's pentane, except this time it's hydroxyl groups at 2 spots. And so in this case, we're going to have pentane. Now in this case, because it's going to be a diol, okay, let's try that again. This here word from should say keep. Sorry, not from. No, not keep. It's going to be drop. Drop. One day I'll learn how to write on my screen as well. Alright. Apparently today's not going to be that day. Let's now try naming this again. Now that I have I was going to give you the right name, but so in this case it's going to be pentane, because the suffix begins with a consonant here. Right, it's going to be pentane-2-diol. And so this all part, the di, begins with an E. That's not a vowel. We keep the E here. So pentane-2, 3, because there's actually, right, 2 of those. Pentane-2-3-diol. Okay. We also have to make sure we name and number any alkyl branches off of the main chain. I'll get you to add 1 bit into here. Name and number any halogens. off of the main chain. Same rules for halogens and alkyl branches in terms of being alphabetical apply. Difference being the hydroxyl groups take precedence. They need to have the lowest numbers. So as another example, and you can try naming this one after I get it written down. That was supposed to be a straight line. Alright. So if we look at this, it looks like that's not a straight line. Let's try again and make that a straight line. Alright, so if we look at this, we have a carbon atom, oops, here, another one here, 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 and here. Now it looks like we've got these two methyl groups, and in terms of numbering, if we do 1, 2, 3, 4, 5, 6, 7, that seems to be, so we have 2, 3, and 7, that seems to be nicer numbering system than if we go 1, 2, 3, 4, 5, 6. So 1, 5, 6 or 2, 3, 7. It seems like 1, 5, 6 seems like it's lower numbers. Doesn't matter. The OH, this alcohol, that takes precedence. And so in terms of naming this thing, and here's where you should pause it and try on your own. Number it off. We have 5,6 dash dimethyl heptane. It's gonna have just a single one, so I drop the E-1-all. There we go. If I wanted to add a chloro or a bromo somewhere, I could have done that as well. I did not. Okay. And again here we want the lowest number for the location of the hydroxyl group. Okay, here's another one. Let's name this guy. Alright, so pause it, give it a try. This is going to be 3-methyl butan-2-all. Okay, here's a little bit more precise set of rules. You can read through that. Right, and then here's another example. Looking for both molecular and structural formulas for alcohols A and B, and then the molecular condensed formulas for C and D. So for A and B, in terms of molecular formulas, normally methanol, and this is what you would have used in our first unit, methanol is going to be CH3OH. And ethanol is going to be C2H5OH. We'll get to our structural formulas in just a second, but those are our molecular formulas. Structural formula, again, pause it for a moment here, give this a try. Okay, so this is not condensed here, what I'm showing. Show all the hydrogens. Now, I drew the stereochemical one earlier in the lesson. I'm showing you the difference here. This is a structural formula. It does not show the geometry, right? That the carbon was tetrahedral and the oxygen is bent. We don't show that here. We don't have to. Okay, so that's for A. For methanol, pause it again. Take a look at ethanol. Okay. Now, some people sometimes wonder, what's the big deal? Why should I care about molecular formulas? Well, molecular formulas are going to, like this CH3OH, C2H5OH, they do tell us a little bit about the structure, but they also tell us, and they make it easier if you're doing a combustion reaction or something like that. The combustion reaction is a lot easier to balance with something like this, where it's easy to keep track of what you have, or this one here, compared to something where you've got it all written out like this and you have to count. Alright, so propane 1-all, in terms of a molecular condensed formula, now we can do a condensed structural formula. A molecular condensed formula is actually what I was doing already here. Okay, so where we're going to have propane 1-all is going to be CH3, CH2, CH2OH. By convention, when we write this out, the alcohol, the hydroxyl group, always ends up at the end, even though if we were numbering this, this would be carbon number 1, number 2, and here would be number 3. Butane 1-all, okay, similar idea, CH3, CH2, 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 and finally ending with an OH. Lovely. All right. Okay. Now, we do have to distinguish, and this is one thing that the curriculum kind of, it gets to this and then kind of just leaves it there. We have to talk about primary, secondary, and tertiary. And what we're talking about with these is basically what position or how many carbons is attached to the carbon that the hydroxyl group is attached to. And this sounds goofy the way I say it. Much easier to see once we look at some pictures. But the big thing here is that the position of the functional group can vary, and as a result, it will alter both chemical and physical properties. Okay. So if the hydroxyl group is attached to a carbon that is attached to only one other carbon, that's this one over here, we call it a primary alcohol. If we look at this one, the hydroxyl group is attached to this carbon, it's attached to 2 carbons, and so it would be a secondary alcohol. And then if we look at this one here, the hydroxyl group is attached to this carbon, it's attached to 1, 2, 3 carbons, and it makes it a tertiary alcohol. So when we name alcohols that have more than 2 carbon atoms, we have to indicate the position of the hydroxyl group, which we've been doing already. Okay. So here we've got a condensed structural formula. I have to tell if it is, first of all, name it and then indicate whether it's primary, secondary, or tertiary. Well, I'm going to actually determine that bit first. So this is the carbon that the hydroxyl group is attached to. It's attached to 1, 2, 3 carbons. This is going to be a tertiary alcohol. Now let's name it. So we have 1, 2, 3, 4, 5 carbons. Off the second carbon, we have the hydroxyl group, and we have the methyl group here. So in terms of naming this guy, it's 5 carbons long, so it's some kind of a pentane, and it's going to be some kind of a pentane 2-all. Well, it turns out it is a 2-methyl pentane 2-all. Now the odd time you will see, and we don't normally have to, but you might see somebody write it this way, and so just to let you know that it shows up. Sometimes they don't write the hydroxyl group as an alcohol. Sometimes they would write this same thing as 2- and instead of calling it an alcohol, it's a 2-hydroxy 2-methyl pentane. Okay, and so they refer to this OH as a hydroxy branch. Normally we don't use that method, but it is possible, and so you need to be aware of it. Okay. So this alcohol is used as a toxin denaturant for ethanol. Now ethanol is the type of alcohol that you'd find in alcoholic beverages, and if a lab is going to buy, let's say 95% ethanol or 100% ethanol because they're using it for some sort of an experiment, 100% ethanol is actually, from what I recall in university, very hard for labs to buy. They have to sign off on all kinds of things that they're not planning to actually use it for some kind of a crazy party. What they have to do normally is you'd buy like 95% alcohol. It means the other 5% is not water, it's going to be toxic stuff, and it'll be denatured alcohol, and this would be one of the things added to it, basically to make it so that it is undrinkable. And the idea there is that it's not being misused. Okay, and so let's look at this alcohol. It is 1, 2, 3, 4 carbons long, and we look and say, oh, 2 and 3 have a methyl group, and the number 2 has the alcohol group. So this guy, pause it if you want, try it on your own. 2,3-dimethyl butane-2-all. Okay. Alcohols that contain more than one hydroxyl group are going to be called polyalcohols. Their names indicate the number and positions of the functional group. Ethane 1,2-diol, also known as ethylene glycol. This is actually found in antifreeze. Propane 1,2,3-triol or glycerol, basis for fatty acids. Okay. Draw a structural formula for butane 1,3-diol, or here's that other method again, 1,3-dihydroxyl butane. Okay, so it's butane, so it's 4 carbons long. Structural, not line, sorry. 2, 3, 4. Pick one of them to be a 1. Let's call this one the number 1. We have an OH there. 2, 3. We have an OH here. This will have an H. So we get all of our H's done up. And away we go. Okay. We can also have cyclic and aromatic alcohols. So if we have C6H11OH would be cyclohexanol. Okay, so basically line structure for that guy. For cyclohexanol, we start with cyclohexane and one of the carbons has the OH attached to it. If we have a benzene ring with one of the hydrogens replaced with an OH, so that's going to be, I'll draw this one over here. That is the worst hexagon I think I've ever managed to draw. It's better. And something like that. An OH would be known as phenol. So, line structural formula for cyclopentane 1,2-diol. Cyclopentane is going to be 5 in a ring, not quite a circle, I guess. And pick 2 of them. Let's call this one 1. And this one 2. Cyclopentane 1,2-diol. Now, we've talked about elimination reactions already. A couple more things about elimination, some specific to alcohols, some is review here. Cracking is an industrial process in which larger hydrocarbons are broken down at high temperatures into smaller molecules. Now, when we start off with already a small one, we can actually have cracking giving us dehydrogenation. And in this case, molecules of hydrogen would be eliminated from ethane. Joffre, which is east of Red Deer, is one of the plants in Canada where cracking takes place on an industrial scale. Alright, so we can have these two guys get bonded together. We're left with a double bond here, ethene instead of ethane now, and hydrogen. Now we can also have an elimination reaction where we have an alcohol. And in this case, we form a bond here. This bond breaks, this bond breaks. We're left with a double bond, and we've eliminated a water molecule. Okay, so elimination can be an alcohol being turned into an alkene plus water. Okay. So if we want to synthesize ethane from ethanol, now this is showing the first step in that reaction. So if we wanted to go from ethanol to ethane, we have to go through this reaction first. So we start with ethanol. We heat it up. It's a catalyst generally. We eliminate the water. And because we're eliminating a water, it's becoming dehydrated, so it's dehydration. We get ethene. And then, to our ethene, if we want to end up with ethane as our final product, we would take our ethene, so here's step 2, and looking back at your reactions that we've done in the past, we do an addition reaction. Addition in this case of just hydrogen, H2, is going to give us ethane. not really added a whole bunch extra, other than we're showing, yes, here is a new reaction with alcohols where we can turn an alcohol directly into an alkene using elimination. And then in this case, you could see it could be part of a process where we start with an alcohol, we end up with an alkane. Okay. One more, and we're going to talk about this here because it doesn't really fit a lot other places. It is a dehydration reaction, but we call it a because we're in science, we like to make big words. DHydro halogenation. So the DHydro is getting rid of a water. We're also getting rid of a halogen. And here we can start with an organic halide, which we were talking about yesterday and Thursday, to form or produce an alkene. So in this case, we actually need an OH minus. This is our hydroxide ion. So we start off with our organic halide, chloroethane. And then we and a hydroxide ion. Now what actually happens here, this is the mechanism, sometimes people see it and it helps them to figure out what's going on. You don't have to know what this mechanism is. But the OH attacks this hydrogen, yanks it away. The electrons that are in here jump to that bond, making a double bond. Well, now this carbon has too many bonds, and so it boots out the electrons there and kicks out the chloride ion. We're left with ethene, right, the double bond between the carbons. We're left with this kicked out chloride ion, there it is, and we're left with water, which forms when this OH minus grabs onto this H plus, or this H here. Okay, and so we can have a dehydrohalogenation reaction where we react the organic halide with an OH minus. It yanks away a hydrogen, okay, to make water, and then the resulting rearrangement forms a double bond, makes our alkene, and boots out the halide ion. So, example, the elimination of a halide ion from an organic halide is the most common method for preparing a specific alkene in the lab. Write a structural formula for the preparation of but-2-ene from 2-chlorobutane in the presence of a strong base. Alright, so we have to start from 2-chlorobutane, so that's what we're starting with. So 2-chloro. We'll get there. Right. Presence of a strong base, OH minus. Okay. So again, that's going to attack. Now, it's telling us that we're going to end up making but-2-ene. And that means that our double bond is going to go from the number 2 carbon to the number 3 carbon. That tells us that this hydroxide is going to attack this hydrogen as opposed to the hydrogen over here. If it attacked this hydrogen, we would end up with but-1-ene. Okay. As it is, it attacks this hydrogen, rips it off. Oops, sorry. Trying to show the bond there, it's not cooperating. So it's going to rip off this hydrogen. Electrons plunk into the double bond, kick out the chloride. We're going to end up with H3C-CH double bonded to a CH to CH3 plus H2O. Right, so that's the OH grabbing onto that hydrogen plus Cl minus. Okay. Next one here, elimination of the elements of a water molecule from an alcohol is the second most common method of preparing a specific alkene in the lab. Write a structural formula for the preparation of but-2-ene from butane-2-all in the presence of a catalyst. Alright, so very much the same. So we've got our OH here. So in the case of this one, this is only a 4-carbon chain. Okay, so again, we're showing the preparation of but-2-ene, and so these are going to join together to make water, and we're going to be left with a double bond in the middle there. So C-CH, double bond to another CH, single bond to CH3, plus H2O. This is an elimination reaction. Sometimes it'll be known as a dehydration reaction. And so here's just some review here at the end, different ways of, or different types of reactions. Perfect, thank you.